Welcome to lecture 2 on circles. In the first lecture, we derived different forms of equations of a circle. In this lecture, we will continue to do that in the starting. So, we will first discuss how to derive the equation of a circle which passes through 3 given non-collinear points. Then we will move on to finding the equation of a circle for which the 2 endpoints of any diameter are given. We will also see how to check whether a given point belongs to the interior region of a circle. We will also derive formulas to find the intercepts of a circle on both the x and y axis. And in between, we will also solve some problems to illustrate these derivations. So, let us start with the following. So, suppose we are given 3 non-collinear points. So, the 3 points are not in a straight line. Then from high school, we know that if we have 3 points and they are not in a straight line, then there exists a unique circle which passes through these 3 points, or basically a unique circle on which all these 3 points will lie. We can always find a unique circle, but only as long as these 3 points are non-collinear. So, they should not be in a straight line. So, let us say that we have these 3 points. The coordinates are x1, y1, x2, y2 and x3, y3. In order to find the circle through which passes through all these 3 points, we basically just need to find out the center of that circle and also the radius of that circle. So, if we can uniquely find out the center and the radius of that circle, then we basically have the equation of the circle. We know one simple result from high school again, that if we have a circle and if we take any chord, for example, the chord here, and let us say that this line is the perpendicular bisector of the chord AB. Then from high school we know that the center of this circle will always lie somewhere on this perpendicular bisector. Many times students are asked the question that suppose if there is a circle, or you are given a circle and you are asked to find the center of the circle. So, the center is not shown here. So, how would you find the center of this circle? So, one way is to use this property. So, what we do is we can just construct any 2 arbitrary chords. So, this is one chord, this is another chord, and then we construct the perpendicular bisectors for both these chords. So, this is the black dotted line is the perpendicular bisector of the chord AB, and this other blue dotted line is the perpendicular bisector of the chord CD. Now, from this property here, we know that the center of the circle must lie on the perpendicular bisector of any chord. Therefore, the center must lie on this, somewhere on this perpendicular bisector of the chord AB. The center of the circle must also lie on this blue dotted line, which is the perpendicular bisector of this chord CD. Since the center must lie on both this black dotted line and the blue dotted line, and these two lines intersect exactly in one place, which is here, we are sure that this point of intersection is the center of this circle. So, this is the basic idea that we are going to use here to first find the center of the circle. So, if there is a circle which passes through all these 3 points, so suppose there is a circle like this which passes through these 3 points, then the straight line joining P1 and P2 will be a chord of this circle. Similarly, the straight line joining P2 and P3 will be another chord of the same circle. And then using the result that we just saw now, we can easily find the center of this circle, because now we have 2 chords. We just need to construct so let this line be the perpendicular bisector of the chord P1, P2. And let this line be the perpendicular bisector of the chord P2, P3. And then of course, the point of intersection of both these perpendicular bisectors is going to be the center of the circle. Once we find the center, finding the radius is very easy. We can just measure the distance between this center and any 3 of these points. So OP1 will be equal to OP2, will be equal to OP3, and all of them will be equal to the radius of this circle. And once we know the coordinates of the center and the radius of the circle, we can write the equation of the circle. So, let us do that in a little bit of detail now. To get the coordinates of the center here, one way is to write down the equation of these 2 perpendicular bisectors and then solve for the point of intersection. So, starting with the bisectors, let this be bisector B1, this is bisector B2. So, this bisector B1 will pass through this midpoint of the chord, and the coordinates of the midpoint is of this chord is x1 plus x2 over 2, y1 plus y2 over 2. Similarly, the coordinates of this midpoint of this other chord P2, P3 is x2 plus x3 over 2 and y2 plus y3 over 2. So, now writing the equation of this perpendicular bisector B1 is not very tough because suppose if we have a point here any point, let us say we have a point having coordinates x and y on this perpendicular bisector B1, then the slope of this perpendicular bisector B1 is going to be y minus y1 plus y2 over 2 divided by x minus x1 plus x2 over 2. Further, we see that this chord and this perpendicular bisector B1 of the chord intersect at 90 degrees. Therefore, the product of the slopes of these two lines will be minus 1. Hence, slope of the perpendicular bisector times slope of this chord, which is y2 minus y1 divided by x2 minus x1 is equal to minus 1. So, if we rewrite this nicely, we will basically get the equation of this perpendicular bisector, because the x and y coordinates of any point on this perpendicular bisector has to satisfy this equation. And if we refine this a little bit, we get this times so this is what we get after we refine this. So, this is the equation of the first, the equation of the perpendicular bisector B1 of chord P1 P2. In a similar manner, the equation of the perpendicular bisector of P2 P3 is going to be, and that we can write straight away because it is going to be a similar expression, y minus times equals 0. And now we just need to solve these two equations simultaneously, because we know that the center of this circle is the point of intersection of these two perpendicular bisectors, whose equations are given by these two equations. So, to find the center of this circle, we just need to solve these two linear equations simultaneously, and let the x and y, which is the solution of these two equations, let us represent that by x naught, y naught. So, y naught and x naught. So, then x naught, y naught is the center of the circle which passes through P1, P2 and P3. Now, once we have found the coordinates x0, y0 or x0, y0 of the center of this circle, So, the radius will be given by r equal to square root of x0 minus x2 whole square plus y0 minus y2 whole square. And as I said earlier, the radius will be the same whether we take this distance or this distance or this distance. And then of course, once we have got the radius and the center, we can easily write the equation of this circle in the center radius form. The other important thing was that why do we really need this condition of non-collinearity of these 3 points? And it should not be very difficult to see that, because let us say that what if these 3 points were collinear. So, if these 3 points were collinear, that is that they were on the same straight line, then we will show that they can never lie on the same circle. If they were to lie on some circle, then the center of that circle must be at the intersection of the perpendicular bisector of both this chord and the perpendicular bisector of this chord, and that we have already seen earlier. But if we see here, the perpendicular bisector B1 of the chord P1 P2 is like this, and the perpendicular bisector of the chord P2 P3, which is B2, is this other blue dotted line. But because P1, P2, P3 lie on the same straight line, it is very easy to see that both the perpendicular bisectors are parallel to each other, because we have a straight line here and this is 90 and this is also 90, and hence these two perpendicular bisectors are parallel, and therefore they will never intersect. And since they will never intersect, it means that there cannot be any circle, because then we can't find a point where these two intersect, because they are parallel, and hence there will not be any circle through which all these three would pass, because if there is a circle from where these three will pass, then the perpendicular bisectors must intersect at the center of that circle. But since they are not intersecting, these two perpendicular bisectors are not intersecting in this case where the points are collinear, it follows that there will exist no circle on which all these 3 points will lie. We will take up a short example to illustrate this procedure. So, in this example we are given 4 points, and we are asked to show that they are concyclic. Concyclic means that all these 4 points, they lie on the same circle. So, one way of showing that is that we take, let us say, the first 3 points and we check if they are collinear or not. If they are non-collinear, then we can find the equation of a circle which passes through these 3 points. Once we have the equation of that circle, we can simply check whether this point, the fourth point here, lies on that circle or not. So, the step 1, the first step is to first find the equation of a circle through which passes through these 3 points. So, one of the points is, if we were to draw the coordinate axis with the origin here. So, the point 1 0 is over here, let us say. So, let us say each square here is of unit length. The point 2 minus 7 will be somewhere on this vertical line. So, it is somewhere here, because this is 7 units. And the third point is 8 1, which is so these are the 3 points. So, as discussed, if a circle has to pass through these 3 points, let us name them P1, P2, P3. Then we can consider these 2 straight lines, which will obviously be chords of the circle which passes through P1, P2 and P3, and we will find out the equation of the perpendicular bisectors of these 2 chords. Let us say bisector B1 and bisector B2, and then we will see where they intersect. So, this point of intersection will be the center x0, y0 of the circle which passes through P1, P2 and P3. And of course, in this case, geometrically we can see that these 3 points are not collinear, and that is why we proceeded further with finding the circle through on which all of them lie. For the first perpendicular bisector, any point having coordinates x, y on B1 will have a slope equal to, so any point xy on B1 must satisfy the following equation. So, the midpoint of this chord here is (1.5) and minus 3.5, and therefore, the slope of this perpendicular bisector is y minus 3.5, which is y plus 3.5 over x minus 1.5. And since this bisector, perpendicular bisector and the chord are at 90 degrees, the product of the slope of the perpendicular bisector, which is this expression, times the slope of the chord P1, P2, which is it will be minus 7 minus 0 divided by 2 minus 1, which is minus 7. The product must be minus 1, and therefore the equation of this perpendicular bisector of this chord P1, P2 is so this is the equation of the line B1, which is the perpendicular bisector of P1, P2. In a similar manner, we will find the equation of the perpendicular bisector of this other chord P1, P3. The coordinate of this midpoint of this chord will be (4.5, 0.5). Now, if we have any point having coordinates x and y on this bisector of the chord, on this perpendicular bisector of the chord P1, P3, then the slope of this perpendicular bisector B2 is y minus 0.5 divided by x minus 4.5. Since this perpendicular bisector and the chord are at 90 degrees, the product of their slopes will be minus 1. Therefore, this times the slope of the chord, which is 1 upon 7 equals minus 1. We have y minus 0.5 equals minus 7x plus 30.5. So, this is the equation of the bisector B2, which is this dotted green line. And now the center is at the point of intersection of these two perpendicular bisectors. There is a little correction here, this will be 31.5. So, from the previous slide we get that the coordinates of the center of the circle satisfies these two equations. And then from these two, what we see is that x naught by 7. So, I take this 3.5 on this side, I just have y naught here in this equation. So, y naught is basically equal to this. Similarly, from the second equation, if I take 0.5 to this side, I have y naught equal to minus 7x naught plus 31.5 plus 0.5, which is 32. So, both these are y naught and therefore, they have to be equal, and then we can get that 50 x naught by 7 equals, so we have to take this on this side. So, we get from where we get that the x coordinate of the center of the circle is 5, and therefore, the from this equation or basically from this equation we have y naught equals minus 7 x naught plus 32 equals minus 7 times 5 plus 32, which is minus 3. Therefore, the center of the circle is at 5 minus 3, and now that we know the center of the circle, so this is 5 comma minus 3, we can easily find the radius. It will be this distance. So, the radius r is, that comes out to be 5 units, and then it is very easy to write the equation of the circle. So, it will be x minus x naught whole square plus y minus y naught whole square is r square. Since x naught y naught is 5 minus 3, we get this as the equation of the circle. R is 5, so r square is 25. So, this is the equation of the circle on which these 3 points lie. And now we just need to check whether this 4th point lies on this circle. So, if we put x equal to 9, y equal to minus 6 on the left hand side, we get so this is 16 plus 9, which is 25. So, the left hand side is equal to the, so the left hand side we computed that the with x y equal to 9 and minus 6, we see that the left hand side is 25, which is equal to the right hand side in the equation of the circle, and hence this point indeed lies on the circle, on this circle which passes through the first 3 points, and hence all the 4 points lie on that circle. So, with regards to the previous problem where we were given 3 points which were non-collinear, and we were asked to find the equation of a circle which passes through all these 3 points. So, apart from the method that we discussed, another method is as follows. So, in this other method, we use the general form of the equation of a circle, which is given by this equation, and we have already seen this in the previous lecture. Since these 3 points lie on this circle, this equation must be satisfied by the coordinates of all these 3 points. Since this equation must be satisfied by the coordinates of the first point P1, if we replace x and y by x1 and y1, we should still get a 0 on the right hand side. Since P1, so this is the circle capital C. Since P1 lies on C, it follows that x1 square plus y1 square plus 2g x1 plus 2f y1 plus c equals 0. And similarly, since P2 and P3 also lie on this circle, we get other 2 equations. So, for P2 we get this equation, and for P3 we get this third equation. Now, we see to completely describe this circle, we have 3 unknowns, and they are G, F and C. And if we see here, what we have is 3 equations, all of them linear in G, F and C. Hence, here we have a linear system of equations in 3 unknowns, 3 equations, and therefore, we should be able to solve it. So, on solving, we will get the values of G, F and C, and when we put these values back in this equation, we get the complete equation of the circle in the general form. We consider another way of describing the equation of a circle. So, suppose that we have a circle where we are only given the 2 endpoints x1, y1 and x2, y2 of some diameter of that circle, and then we are asked to find the equation of this circle. So, one way to do that is, if we again go to our high school geometry, then we know that if we have any point xy on the circle, on the circumference of the circle, and if we connect this point to the two end points of this diameter, then we know that this angle here is always 90 degrees. So, we will use this property to derive the equation of the circle. Since the angle here is 90 degree, the product of the slope of this chord times the slope of this chord should be -1. The slope of this chord is y2 minus y over x2 minus x times the slope of this chord is y1 minus y over x1 minus x, and this product should be -1, and then if we rewrite it nicely, what we get is x minus x1 into x minus x2 plus y minus y1 into y minus y2 equals 0. So, as we can see this, if we expand this further, then we will see that we get this equation x square plus y square minus x1 plus x2 times x minus y1 plus y2 times y plus x1 x2 plus y1 y2 equals 0. And this is exactly in the general form of a circle, which was x square plus y square plus 2gx plus 2fy plus c equals 0. And by looking at it, we can also find out the coordinates of the center and the radius of the circle. So, the center is minus g, and minus g will be x1 plus x2 over 2 comma y1 plus y2 over 2. So, the center is minus g comma minus f, and g, by comparing these two, g is equal to minus of x1 plus x2 over 2, f is minus of y1 plus y2 over 2, and similarly we can find the radius also. Lastly, let us take this problem of how to check the position of a point, of an arbitrary point with respect to a circle. So, suppose we are given some point whose coordinates are a and b. So, we have a point P with coordinates a and b, and we have a circle whose equation in the general form is x square plus y square plus 2gx plus 2fy plus c equals 0. So, now how can we tell whether this point P lies inside the circle or it lies outside the circle? So, geometrically, if we see this circle, then we see that the circle has center at minus g minus f and radius equal to square root of g square plus f square minus c. Now, if this point a comma b is somewhere there on this plane, so if this point a comma b is inside this circle, let us say here, then it is clear that the distance between this point P and the center will be less than the radius r. So, P is inside the circle if and only if the distance between the point P and the center of the circle, which is this, is less than the radius. So, the radius is and if we simplify this further, then this condition is essentially equal basically a square plus b square plus 2 ag plus 2bf plus c is less than 0. But if you see, this left hand side is nothing but this second degree equation here with x equal to a and y equal to b. So, to check if the point is inside, if this point is inside, we just replace x and y by the coordinate a and b respectively, and then we check if the value that we get, if it is less than 0. If this value, after replacing x and y with a and b, if the value that we compute is less than 0, then it means that the point is inside the circle. Similarly, if the point is outside the circle, then the distance will be greater than r, and then the condition that we will get is that again this value here should be greater than 0. And then of course, if this point P lies on the circle, then this will be exactly equal to 0. So, these are the three scenarios. Given a point a comma b and a circle C having this equation, we will first compute this expression with the coordinates of the point P. So, we get a square plus b square plus 2ga plus 2fb plus c equals. So, if we replace x with a and y with b in this left hand side, we get this value here, and then we check this value, because this value will be either positive or negative or equal to 0. Now, if this value equals 0, so if equals 0, then it follows that P lies on the circle C. If this value is less than 0, then it follows that P lies inside C. And finally, if this value is greater than 0, then it follows that point P lies outside the circle C. So, if this is true, then P lies outside the circle C. So, with that we will finish this lecture. In the next lecture, we will continue with the other topics like finding the intercepts made by a circle on the axis, on both the axes. We will also derive conditions to check whether a line passes through a circle or it does not, or it passes through the center of the circle or not. And we will also take up some problems. Thank you.